Here's a summary of what we've learned so far. I've added that you should now know what the speed of a wave is, and you should be able to calculate the speed of a wave by using that equation. So now we want to talk about what intensity is. And notice that intensity is related to the amount of power produced by an object. So I guess we need to first to redefine what do we mean by power. So power is given by a cursive letter P, and it is the amount of energy given off by something per unit time. And so energy is going to be given in terms of joules, and then time is given in seconds. And then when you put those two things together, a joule per second is the same thing as a watt. So 1 watt is 1 joule per second. And that's what we mean by the power of an object. It's related to the amount of energy that it gives off. So notice that intensity, which is going to be given by the letter I, is going to be equal to the amount of power that something gives off, but it also depends on the area that it goes through. So A is for area. And so this is going to be the brightness of a light bulb. So when we talk about the intensity of a light bulb, we're talking about the brightness of the light bulb. And it's going to depend on the wattage of the light bulb, and it also depends on the area that it passes through, which means it depends on distance. So that, in this picture that is down below it, let's take a look at this, where we've got a light bulb that is giving off light. Now let's pretend that we are going to be located a distance r away from the light bulb. So if we're right here, let's pretend that we've got a window. Okay, and now this window is going to have a certain area A, and some of this light is going to pass through that window. Okay, now let's pretend that we go 2 times further away. So now we're going to be at 2r is going to be the distance from here over to here. Now this light is going in all different directions. So can you see that some of the light is going to go like this? Now let's pretend that we want to still capture all of the light that went through this window. But notice that it's spreading out the further away it gets from the light bulb. So that means in order to capture it over here at a distance of 2r, it's going to take 4 times the amount of area in order to be able to do that. Okay, so this time we're going to have 4 times the amount of area is going to be required in order to be able to catch all of this light that's coming from here. And then if you go 3 times further away, it turns out that you're going to need 9 times the amount of area. Now I want you to try this experiment with a flashlight. So if you take a flashlight and you hold it, let's say 10 centimeters away from a wall, and you turn it on, it's going to make a circle on the wall. All right, now if you back away, so it's 20 centimeters away from the wall, so twice the distance, you're going to notice that that circle has gotten bigger. And that circle now will have 4 times the area that it did when it was only 10 centimeters away. But you ought to notice something else. What do you notice about the circle? It got dimmer. Did you notice that? So the further away you get from the wall, the bigger the area is getting, but the smaller the intensity is getting. And so you can see that that's given by this little formula right here. So the intensity I is going to be proportional to 1 over r squared. Okay, and remember, what is the area of a rectangle? It's going to be length times width. So that's the reason for the squared thing. So the squared thing is telling you it's the area that it's traveling through. All right, so here's the kind of question that I would like for you to be able to tell me on the exam. If you get 6 times further away from a light bulb, how does its intensity change? Now, first of all, I'm going to give you partial credit if you say it gets dimmer. Okay? You saw with the flashlight, you pull it away from the wall, it gets dimmer. So that's something that I'd like for you to know. Okay? Now, if you say it got 6 times dimmer, well, that's better, okay, than just saying that it got dimmer. But it's not quite right, because what did you forget to do? It's r squared. So you need to take the 6 times 6 is 36. So you could say it's going to be 36 times dimmer, or you could say it's 1/36th as bright as what it once was. So either of those two answers would be okay on the exam. Now, there are other kinds of intensities. So we have just talked about the intensity of light. What about the intensity of sound? So that's going to be given by a thing called the decibel. So sound intensities are measured in decibels. And so this chart here shows that you can just barely hear something, a sound wave, if it has a decibel of 0. The rustle of leaves has a sound intensity of 10 decibels. And then it goes up from there. And then the last column is telling you what is the intensity in watts per meter squared. So the last column is the official metric unit for intensity, but the decibel system is a shorthand way of telling you how loud something is. What about an earthquake? So an earthquake can also have an intensity. The closer you are to the epicenter of an earthquake, the stronger the shaking is going to be. The further away you get from the epicenter of an earthquake, the weaker the earthquake gets, because intensity is proportional to distance squared. So the further away you get, the weaker an earthquake is going to get. So the intensity scale that is used for earthquakes is called the Richter scale. And it goes from 0 to about 9 or 10. So we don't think that you can actually get to a magnitude 10 earthquake because the rocks would shatter. But we've gotten awfully close to that. And so this chart here shows you the different numbers on the Richter scale. So that's going up and down. Over on the far right is showing you the intensity in terms of the metric system. And then in the middle, it shows you how many earthquakes of that magnitude occur every year. And most of those earthquakes you don't feel, because you just don't feel the earth vibrating. But it really is. All right, let's take a break, and when we come back, let's talk about how do waves interact with matter.